So for the last little bit today, I'm going to be talking about an architecture called Intel Xeon Phi, which has been recently released. We had hoped that during this workshop we would actually be able to let you guys actually use some of these devices because they've only very recently been released. So we had, and this is one of the reasons why we pushed the date for this workshop back from the originally planned date, because we had ordered a system which had, 12 nodes, I think, with these KNC cards in them. But things didn't really run to schedule, so we haven't been able to show you, but I thought it might be good just to tell you a little bit about this architecture. So before we start, it was only publicly unveiled at the Supercomputing conference in November, so about a month ago. And the first commercially available cards are being delivered out to sites like us at the moment. So Intel hasn't been letting too much information out into the public domain. But when they do, they've got a website where they have information for people interested in developing codes for Intel Mic. So at the moment, it's mostly full of marketing talk, but there is some interesting information buried in there. Because I think for every software engineer or engineer at Intel, and there's a lot of them, there are two marketing people, so you do have to be careful. But they do have some very good guides actually. I already gave you this link in another talk. It's a guide for getting ready to port your code to run well on Xeon Phi, and it's got a lot of very good information, and one thing I can definitely say is if you follow a lot of the guidelines in this, you will end up with code that runs very well on Sandy Bridge as well, because a lot of the things that you have to do on Sandy Bridge that is nice to do on Sandy Bridge to make your code run well, you have to do on Knight's Corner to make your code run well. So it's definitely worth looking at this document. So what is Xeon Phi? So who here has heard of it? It's also been called the Mic for Many Integrated Cores, or KNC for Knight's Corner. I think this is a much nicer name than Xeon Phi, but that's just my personal preference. So how many people have heard of this architecture? Okay. Oh. Yes, certainly. You will certainly be able to buy it, but I don't know if it... Yeah, it's not. I mean, their target market is not just a normal desktop PC user. I think the lowest end target user would be people with high performance workstations who might be able to take advantage of this. But it's I don't think you get an awful lot out of just plugging it into your games PC. So it's a plug-in coprocessor card. It's based on the x86 architecture, so that same architecture that's behind our Sandy Bridge and our many generations of Intel chips before it. But the main departure from history is that it has between 50 to 60 cores. I think the number has been finalized at 60 cores. We've had some test devices here for a while that have had 61 cores. It has a fully coherent cache memory model. That means each of these cores has its own cache, and it maintains coherency between the caches, and it communicates with a host CPU via the PCI Express. And it's designed as a coprocessor for suitable computational tasks, and suitable is the key word here. It's not going to accelerate your... it's designed to be very good at certain tasks in lieu of not being good at some other general computational tasks. So here's just some general some specifications. It has 60 cores, and each core can support up to 4 hardware threads. So you can have a total of 240 threads on this thing. It has a coherent cache, so each core has its own L1 and L2 cache, and Neil spoke earlier about cache coherency, and unlike on GPUs, which don't really have anything like cache coherency, this actually maintains fully coherent cache. So if a value gets updated in the cache of one CPU and it's in any other CPU, and that same cache line is in any other CPU's cache, it will also update that cache line. It has 512-bit vector registers. Now this is very important because SSE instructions had 128-bit, so you could fit 2 doubles in a single vector register. Sandy Bridge and Ivy Bridge will have 256-bit vector registers, so you can fit 4 doubles. But this has 512-bit vector registers, so you can fit 8 double precision values in one register. And that means you can fit 16 single precision values. And this is really, this shows vectorization becomes very, very, very important on an architecture like this, because it can do 8 double precision operations in a single clock cycle if you've got your vector register properly loaded. But if you don't do your code correctly and you only get serialized code, you're only going to be able to do 1 operation per clock cycle, and you're only going to be getting potentially 1/8 of the theoretical performance of this device. So vectorization is very important here. You have 8 gigabytes of RAM on the device, but some of this is used by the operating system that runs on the card. So you might typically only see something like 6 gigabytes of RAM for your application. And it's important. An important thing is that it's a unified memory address space. So it's not a NUMA scheme, it's unified, so every core has equal access to the memory. There's no partitioning of the memory into different memory spaces. And it has a very high memory bandwidth, about 170 gigabytes a second measured. Now, so that's running the stream benchmark, we get 170 gigabytes a second. If we run the same stream benchmark on a Sandy Bridge socket, we get about 35 gigabytes a second. So you can see that it's got very high memory bandwidth and these wide vector registers. So it's designed for these sorts of tasks where you want to load in large amounts of information and process it sequentially using vector registers. And it runs its own stripped-down version of Linux. So when you can actually SSH onto one of these cards and run your applications. You can run GDB to debug on the card. You can have a lot of fun playing around on them. So the obvious comparison people are going to make is Xeon Phi versus GPUs, and there's a lot of similarities, but there's also some very key differences. So both currently require a host CPU. So when you have it, you can't just use a Xeon Phi as a standalone computer. It's got to be plugged into a compute node that has a host CPU, and that's the same for GPUs. And they both communicate with the host and with the communication network via PCI Gen 2. And they're very fast at data parallel computational tasks. Things like matrix multiplication, dense linear algebra, operations like the stencil operations, they can perform very, very, very well. But they've sacrificed general performance to get very good performance for these specific tasks. So if you try to run a code that's not well suited to this architecture, then you're going to get very poor performance. And they also have a mode you can allow the host CPU to offload work to the device. So your application might have some serial parts which are not well suited to running on a GPU or on one of these Xeon Phis. They can perform those tasks, and then they can just pass the computationally intense parts that are well suited to execution on the device to the device, and it will run them. But there are some interesting differences. The first is it's based on x86 architecture, which feels quite familiar. They have a fully coherent caches. I spoke about this earlier. And you can get an OpenMP code that's written for your Sandy Bridge, And you can compile it to run on the Knights Corner natively with little or no modification. And I've found this with quite a few codes. You just use the Intel compiler, you pass an extra flag, and it compiles. That doesn't necessarily mean that it's going to run very well. You might have to make modifications to get good performance. But porting code is not, at least making the first step in porting your code isn't too hard. And they also have some alternative methods, modes of operation besides the offload mode, which I'm going to go into now. So there are three main programming models of which these two are kind of combined. The first is native. So the first native mode means you just take your code, you recompile it to run directly on the card, you copy it to the device, and then you execute it. And it sees an x86-based computer with 60 cores and 240 threads. And you just use the card as a separate computational device and copy your results over at the end. There's a symmetric mode where you use the coprocessor as a node in an MPI cluster. So you start some MPI tasks on your host, like the Sandy Bridge, and you start some MPI tasks on the device, and then they use the normal MPI communication protocols that Neil was just discussing to communicate between them. And then you can, of course, have multiple nodes with devices on them, and in theory, once the technology matures some more, we'll be able to have all of these devices communicating to each other. And the third mode is offload mode, where you take your code and then you add some directives, similar to OpenMP directives, that tell the compiler, hey, this bit of work, I want you to offload that to the device, please. And there's also a final mode where you can use the Intel math kernel library. The math kernel library has been optimized for Knights Corner, so you can turn it on to basically automatically detect that there's a KNC, and it will make the decision when to pass a work off to the device or when to keep it. So if you give it two small matrices to multiply, it will keep the work on the host and do it there, because it's not worth the effort of copying information to the card and bringing it, and then performing the operation and copying it back. And then once it figures that it's worthwhile copying information to the card to process it, it will do so and then get the answer back. So native mode, this is the way, because we haven't had access to the device for very long, so this is the way that we've been running most of our codes, because it's the easiest way to do it. You take your source code and you just recompile it with the Intel compiler with a new flag. And so this is your old source code. If you'd been compiling it, it's an OpenMP code. If you compiled it to run on Sandy Bridge, this would be something like your code, the line you would use for the compiler. If you want to compile the same code for the Xeon Phi, you add this additional flag. And then you can run the executable directly on the device. So the whole program is run on the device. Now this is a problem because a single thread and Neil was talking about Armadale's law earlier, a single thread on this device runs much more slowly than a single thread on something like Sandy Bridge, and this device gets its benefit from having so many cores and so many threads that when it can use all of them at the same time, it's very fast. But Armadale's law actually starts to kick in much faster on this device because the serialized parts of the code run on a very slow serial thread. But we can get around this to a certain extent by running MPI and OpenMP on the device. I was going to show you a little example that I did where we did a Monte Carlo simulation that was very easy to parallelize using OpenMP and MPI. And we found that we could, instead of running with 60 cores, if we used MPI to have two 30-core jobs, we actually got perfect scaling from like a 60 times scaling on the device. Now, if you want, and to compile it to run with MPI OpenMP on the device, they provide some wrappers for the Intel compiler. So it's very similar to compiling just for the device. You just use the MPI ICC. Symmetric mode means you basically take the same or maybe different source codes, MPI codes, and you compile one version for running on the host, say your Sandy Bridge, and one version for running on the mic. So you compile one for the mic oh, and this should be .host, sorry. So basically you create two executables, one for the running on the device and one for running on your host processor, say Sandy Bridge, and then this should have been host. And then you can use the MPI exec command to launch your MPI job. Now I'm going to launch this job with two devices, so I've got mic 0 and mic 1, and then the local node will be my local Sandy Bridge, the Sandy Bridge cores. So on each device you run with I'm going to have 60 MPI tasks on each device and then 16 on the host. And this is quite a nice idea when you first think about it, but we find a big problem with this is load balancing. Because, as I said earlier, a single thread on Xeon Phi runs much more slowly than a single thread on Sandy Bridge. So trying to break the work up into chunks such that both the device and the host will be able to finish their allotted chunk of work in roughly the same amount of time becomes very difficult. And particularly because for some problems, like the Monte Carlo problem, it's very easy to just break up your problem into whatever size chunks. But if you're doing, say, a weather simulation which imposes quite a strict block size that you can process using MPI, it can become quite challenging to utilize 100% or even 90% or 80% of the resources that are available to you. And the final mode is offload mode, and this is the one that's most similar to programming for the GPU. And to do that, you run the code on the Sandy Bridge, and then you offload the parts of the code that are well suited to execution on the device. And this is the best option if you've got a code that maybe has a lot of serial sections in it that aren't well suited to running on the device. And yeah, so you have your fast host thread forms the serial parts, and you can also overlap the serial and parallel sections if that's possible with your algorithm. But this approach, we haven't experimented with it so much. I've got an example that Gilles worked on that I'll show you in a bit, because it actually requires that you go through and make some fairly significant changes to your code, because you have to go through your code and add some directives that look very similar to OpenMP directives that tell the compiler, this part of the code I want you to process, I want you to make run on the device. How many people have seen OpenAC? Are you familiar with OpenAC? Okay, so OpenAC is it's a standard, an attempt at a standard that's been out for a year and a half now. Yeah, it's a bit over a year, yeah. So, and it's an attempt to add some OpenMP style directives that you can use to make code run on the GPU. And the commands look very similar to OpenAC, very similar philosophically. So if you've actually ported some of your code to OpenAC already, then porting it to offload mode on the KNC is not too difficult. I'm sorry if I keep on mixing up the terms KNC, mic, and Xeon Phi, because we've been calling it KNC for months now, and then they went and changed the name on us recently, so we're still adjusting. And to build for offload, you add the directives to your code, and then you just pass this flag to the compiler. And then if you want to run the same code just on the host, you just change the flag to no offload. So and here's an example of matrix multiplication, matrix multiplication. So if you were a simple OpenMP implementation would not have this pragma here. It would simply have these two OMP statements around the loop. So the first one zeroes out the loop that we're going to be, the matrix that we're going to be writing into, and then the second parallel loop takes actually performs the matrix multiplication. And on Knight's Corner, you can take OpenMP code like this, compile it, and it will run fine. Now, to tell the compiler that we want to offload this work, you can add a statement like this. So this is saying pragma, offload, we want to offload this. What's our target going to be? It's going to be mic, and then you can specify in here which mic. If you have multiple cards, you might have only one card, you might have 2 or 4 devices. You can tell it, you have the ability to tell it exactly which card you want to offload to. And you're telling it that you want to, because because this data is currently residing on the host, in the host memory. You have to tell it to copy. You want it to copy this data from the host to the device, and then at the end, you want it to copy the result, the C, back to the host. So they're relatively simple directives. Of course, the devil's in the detail, because once you do that, you might find that it runs on the device, but you actually then might find that what works well on Sandy Bridge doesn't work well on KNC, and you might have to go through and restructure your algorithm. And yeah. So just to summarize, there's three different ways there's multiple ways to build. If you have a code that has mic directives in it and you just want to run it on Sandy Bridge, you use no offload. You can use offload build. We'll compile a code to run in offload mode. Or if you just want to run the program on the mic, you use this -m mic flag. So it's quite flexible in the different ways that you can use it. And currently we're trying to figure out exactly which ways are viable and useful, or which ways are suited to different workloads. So I've just got a couple of case studies. I had hoped to have some more for you, but I ran out of time. But so we just show a little summary of some of our experiences here at CSCS. And I want to put a little disclaimer here, because we've been working with some engineering samples that were sent to Intel by us some time ago. So they're certainly not the finished product, and there have been little bugs and glitches as you get when you have engineering samples. And we've also been using like alpha and beta release versions of their compilers. So we expect that performance of these devices will get better. And also, people haven't really figured out how to program them effectively, or the best way to really go about using them yet. So as the technology matures and we figure out how to get the most out of them, we'll see better performance. So the first is a bit of work that Gilles did, where he looked at dgemm, is one of his favorite topics, and he looked at offloading dgemm on the Xeon Phi. So dgemm, he uses the dgemm that's implemented in the Intel math kernel library. So that's Intel's highly optimized library that has lots of linear algebra operations like dgemm, but also many other useful mathematical operations. And he writes a little wrapper here. So this wrapper function wraps around a call to the dgemm, and you can put this statement in front of a function. This is another way of saying I want you to offload this work. You say, I want this to target the mic. And then when you want to go and call this function, you give it this argument that we saw earlier, pragma offload target mic, and then you tell it I'm copying in the matrices A and B, and then I'm going to copy out the result C that we get at the end. And it also wants you to copy out record the time taken in here. So we copy out the time that we record at the end. So the Xeon Phi that we were testing on had 61 cores, 4 hardware threads per core. So that makes for a total of 244 cores. So we run the code with a 10,000 by 10,000 by 10,000 matrices, they're square matrices, and we get we get 285 gigaflops, which is not too bad. When you consider that I think on a single Sandy Bridge socket has a peak, you'll get a peak of about 160 to 170 gigaflops. So we're beating a single Sandy Bridge socket. But the single Sandy Bridge socket, when it's getting 160 gigabytes a second, it's got a peak theoretical capability. It's getting about 90% of its theoretical capability. So then we say, well, what's the peak theoretical performance? And we do this little bit of maths. How many cores have we got? How long are the vectors? How many operations can we do per cycle? And the frequency of the chips. So we got 1.1 gigahertz chips. We can do 2 operations a cycle. The vectors are 8 doubles long, and we've got 61 cores. And we end up with this is what we figure would be, if we were to to utilize the machine perfectly efficiently, this is what we should be getting. So we're at about 1/4. Yes?
So when you said that one single thread would run 10 times as slow, how does it come out from the code speed? Or is this an experience?
It's a heuristic. It's more of an experiencing it. Though your mileage will vary depending on it. This is what Intel say you should be aiming for getting, a single thread, relative single thread performance. If you then want to get the Knight's Corner to scale really competitively compared to a Sandy Bridge socket. But that's a very rough heuristic. I mean, it depends on your algorithm.
So how can one understand why it's really a factor of 10 when the clock speed is only
because the architecture went from a big stick. Pentium stick. Okay, so you should expect the same difference as on the bridge and not using the open source. So that's roughly
And you've got to remember that you're never going to see linear scaling. You're never going to say, oh, this ran at speed X for one thread, so I'm just going to divide that by 240 and get the total speed for 240 threads. The scaling most certainly isn't linear. We'll see an example of that in a bit. So we see this is our theoretical, and this is what we're getting. We're only getting about 1/4, a bit over 1/4. So whatever happened to the performance? So affinity is very important. Now, this is a unified memory architecture, so we don't have to worry about NUMA effects. But because we've got so many threads and so many cores, the order in which threads are assigned to cores can have a very big impact on performance. So there are 3 different affinity settings. You're familiar with the scatter and the compact affinity setting. And we can see that going from scatter, typically on a Sandy Bridge, scatter will give you the best performance. But we see here the compact affinity actually is, well, it's not double, but it's a lot more than the scatter. And that's to do with once you've got 4 threads running per core, if you use compact affinity, you will have the first 4 threads. So thread 0, 1, 2, 3 will be on the first core. And then the next 4 threads will be on the next core. So you might get better data locality. And balanced affinity is a new type of affinity that was added just for the Knight's Corner. And it's similar to scatter, however, it produces better clustering like this. And it's equivalent to using compact when you fully saturate the device. So we see we've gone from 250 to 640 just by playing around with our the affinity setting, which is a pretty big deal. So we're over halfway to the theoretical peak performance. Now, the alignment of arrays, and this is a general rule for SSE or for AVX, you should try to align your data fields to be aligned with the size of one vector register. So on the Sandy Bridge, which has got a 256-bit vector registers, that's 32 bytes. Arrays should be aligned on 32-byte boundaries. For Xeon Phi, we need to align on a 64-byte boundary, which is a whole cache line. And we'll consider that array's alignment. Okay, there's a bit of a grammatical problem there. But basically, what will happen if you just allocate memory on the host and then copy it over to the device, the operating system will assume that you want the same alignment you had on the host on the device. So if you don't have your data lined up correctly on the host, then it won't be lined up for optimal performance on the device. So we can use this, instead of using malloc, you can use this function mmmalloc. There are actually quite a few different methods provided that you can use by the Intel, which you can use to do aligned memory allocations. You can also use imalloc and mklmalloc. And basically, you don't just say how much memory you want, but you say what alignment you want. So we would say, I want alignment of 64 bytes. And then, so this is what happens when we set alignment to be equal to 16. We get the result we had before. Then when we set alignment to 64, we get another, whatever that is, 10%. Another 10% speed up. So we're getting closer. So this is 13%. I actually figured it out in a calculator. So we're getting to 724. We're getting a lot better. The final step is to see what would happen if we were to use large page sizes. So you can set this environment variable. And what this environment variable says, you basically set a threshold. You say, if you're allocating a lump of memory that's bigger than 100 megabytes, this value here, use 2 megabyte pages, or use huge pages only then. And the matrices, the 10,000 by 10,000 matrices that we're using are definitely much bigger than 100 megabytes. Then when we run the code, we get 806 gigaflops. So that's about 75% of peak performance, and that's the best we've managed to get now. And it's very interesting because we didn't have to go rewriting any code. We were just calling a highly optimized library provided by the vendor, but we still had to go through the steps of really looking closely at affinity, your memory alignments, and your huge pages. And this has a much larger effect on the Xeon Phi than it does on Sandy Bridge, in my general experience. A final little example I want to look at is something I've been working on, and this is just to illustrate some of the difficulties you can have with load balancing. So Cosmo is a numerical weather and climate code that's used by weather services in Switzerland and Germany, Italy, Russia, South Africa, Indonesia. Lots of different countries use this code. It's not only used for weather, it's also used for climate simulations at ETH and lots of other universities. Originally, it's based on an MPI-only Fortran code that was developed for NEC vector computers. So if you go through the Fortran code, you see a lot of design choices that were made for these old NEC vector machines that don't run particularly well on modern multi-core and many-core processors. But the problem is that it's currently used on a lot of these machines. The German weather service, the DWD, they still use NEC vector computers, so the code hasn't moved on from this old format. But there has been an effort, spearheaded mostly by people in Switzerland, to rewrite the code to run better on using OpenMP on multi-core and many-core processors, and also on GPUs. And this rewrite has multiple backends targeted at different hardware architectures, and we looked at porting it to the Xeon Phi, which basically meant recompiling it. And it uses a regular structured 3D grid, so it's the sort of operation that should be quite well suited. And the way the library works is it divides our subdomain into blocks and then distributes the blocks amongst OpenMP threads. So you have one thread per block. And a really interesting problem we came up against was typically you have something in the order of 256 or 512 blocks in a subdomain. So we use MPI to break the global domain up, and then each little subdomain will have about 256 to 512 blocks. And you've only got 8 cores in a Sandy Bridge socket, so it's quite easy to distribute, get really good load balancing, dividing 8 into 256. You've got plenty of work to keep all of those 8 cores very happy. But on Knight's Corner, where you have many cores, this load distribution becomes quite difficult, particularly because the number of cores or number of threads we're using is going to be a multiple of 60 because you have 60 cores. And 60, typically, things are usually end up being designed to divide into powers of 2, and 60 isn't a power of 2. So here we see the scaling on this is a single Sandy Bridge socket. So up to 8 here, we're basically this is for 2 threads, 4 threads, 8 threads. And then this last little speed up here is when we then use hyperthreading. So we're using the second thread on each core. So typically, if you've got a good code that scales well, you don't expect to see much benefit from using the additional cores. But you see, we have quite good scaling up to 8 threads. It's about 7 times. And then this is a comparison. Just ignore the solid lines for a moment. But this is a comparison of what happens when you get a subdomain that has 64 blocks or 192 blocks that is, the number of blocks doesn't evenly divide into 60. And you see that here we only get scaling up to 32 cores, and then the performance drops off. Because what happens is you would give some work. Like here we might give, if we have 64 blocks, for example, and we have 60 threads, each thread will get 1 block each. They'll process them, but then there will still be 4 blocks left remaining. So 4 of the threads will then pick up the final 4 blocks, and the other 56 threads sit there idly waiting for the first, for those final 4 threads to finish working. So you only get about half efficiency there. So this is what happened when I went and changed the block dimensions to make it so that we actually had a multiple of 60 blocks. So I tried for domains that had 60, 120, 180, and 240 blocks. And you can see that for each case, we get very good scaling. It's linear scaling. It's not quite perfect, but it's still very good scaling, speed up to 60 threads. And then when we have only 60 blocks, if you try to add more threads, your performance actually goes down because you're trying to allocate more threads than you have bits of work to pass around. So you should really just stop at 60 threads. If I have 120 blocks, we get good scaling up to 120. The scaling starts to drop off here because up to this point you're assigning 1 thread per block, and then after this you're then putting 2 threads per, 2 threads per core. So you're starting to saturate the cache in the bandwidth. And you can see that as you increase the number of blocks, so 180 blocks scales well up to 180, and then 240 scales all the way up to 240 threads. It has a bit of a dip here because 180 can't divide into 240. But so this was very interesting because when we first looked at it, we said it's not scaling very well. We're not getting anywhere near peak performance. And then we went back and looked at had a closer look and realized we had this load balancing issue. So this was just a very short presentation just to kind of give you an overview of this technology and to show how some of the things we've been talking about during this course about affinity and alignment and load balancing, how they become more and more important as you increase the number of cores. And it's not just with things like Xeon Phi that we're going to see increasing numbers of cores. It's going to be with just the normal pro CPUs we have. They're going to see more and more cores. We're going to have to figure out how to get more and more performance out of them. So these issues will become much more significant in the future. Unfortunately or fortunately, because it makes life harder for people who have to program them. Okay, that's that. Has anyone got any questions?
Just related with the Sony and this one. What makes this one the number of cores? You said 1 core is not.
It's the memory, yeah, the
What about
memory bandwidth. It has much more memory bandwidth. Yeah, it has
we have a problem with 30 threads. Does Sony win of the other one?
30 threads.
30, but let's say 30 with a capacity Sony.
Yeah, but if you're using 32 threads on Sandy Bridge, you're using hyperthreading as well, so you've got 2 threads per core. 16.
Is it still 10 times faster on the Sandy Bridge?
It depends on your code. No, because I mean, usually if you've got a well-written code, it won't. If you see a code scale perfectly from 1 thread to 16 on a Sandy Bridge, your code's probably not that efficient because hopefully you should start to maximize you should reach your peak bandwidth before you've used up all of the cores.
Of course,
But
it's like this one is not going to
yeah.
perfect speed. But I mean, compared to the Sandy Bridge, to the KNC, it's not also.
I mean, we'll see. Yeah, I know, but the KNC does tend to get better scaling as you add more threads. This is 2 threads per core. This is 3 threads per core. We get better scaling than we see over here. I mean, this is if you've got an efficient code on the Sandy Bridge, it won't scale much when you add hyperthreading. But we do seem to get better scaling once we add more threads. But yeah, that's why we need the 10 times. That's why you want your Sandy Bridge to be no faster than 10 times for a single thread, so that when we scale up, we can start to be competitive with the Sandy Bridge. Yes. Don't know. I don't know if they've actually released the OpenCL compiler yet. It's all very early days. I know they're going to support it. I think it was end of this year, start of next year that they were going to release the SDK. Okay, it's just been released. So we certainly don't have any performance numbers for you on that.
When you started the job with how you use this minus host, how do you talk with the is it like network protocol with the host and the
Yeah, it's no.
is it kind of network protocol?
I don't know. Let's see. Yeah, you're giving the addresses here. Where is it? Symmetric mode. Here we go. So this is actually a normal. This is a typical way that you can, when you use MPI run, if you want to specify multiple hosts, you can do it this way. I don't know too much about the network protocol or how the communication is actually performed, but this will be performed over the PCI Express, and then in theory, communication will also take advantage of the QPI
Yeah, of
between.
course, everything is done locally, but emulation of the network.
I don't know.
Let's say if one node, one KNC or one host wants to talk to the other one, so does it have to?
Or like on another host. I don't know. Apparently there is support for using InfiniBand, but I don't know what the status of that is. Communication between multiple nodes, KNCs on multiple nodes. In theory, at least, you can do it. You can have direct communication between two devices, but I think they're still working on really ironing that out and making it work properly. We got any more questions? Yeah, it wouldn't. I don't think you'd get an awful lot out of just plugging it into your games PC. So it's a plug-in coprocessor card. It's based on the x86 architecture, so that same architecture that's behind our Standard Bridge and our many generations of Intel chips before it. But the main departure from history is that it has between 50 to 60 cores. I think the number has been finalized at 60 cores. We've had some test devices here for a while that have had 61 cores. It has a fully coherent cache memory model. That means it keeps, each of these cores has its own cache and it maintains coherency between the caches, and it communicates with a host CPU via the PCI Express. And it's designed as a coprocessor, so about a month ago. And the first commercially available cards are being delivered out to sites like us at the moment. So Intel hasn't been letting too much information out into the public domain. But when they do, they've got a website where they have information for people interested in developing codes for Intel Mic. So this, at the moment, it's mostly full of marketing talk, but there is some interesting information buried in there. Because I think for every software engineer or engineer at Intel, and there's a lot of them, there are two marketing people, so you do have to be careful. But they do have some very good guides, actually. I already gave you this link in another talk. It's a guide for getting ready to port your code to run well on Xeon Phi, and it's got a lot. You will certainly be able to buy it, but I don't know if it... Yeah, it's not. I mean, their target market is not just a normal desktop PC user. I think the lowest end target user would be people with high performance workstations who might be able to take advantage of this. but it's very good information. And one thing I can definitely say is if you follow a lot of the guidelines in this, you will end up with code that runs very well on Sandy Bridge as well, because a lot of the issues, things that you have to do on Sandy Bridge to make that it's nice to do on Sandy Bridge to make your code run well, you have to do on Knight's Corner to make your code run well. So it's definitely worth looking at this document. So what is Xeon Phi? So who here has heard of it? It's also been called the mic for many integrated cores, or KNC for Knight's Corner. I think this is a much nicer name than Xeon Phi, but that's just my personal preference. So how many people have heard of this architecture? Okay. Oh. Yes, certainly. So for the last little bit today, I'm going to be talking about an architecture called Intel Xeon Phi, which has been recently released. We had hoped that during this workshop we would actually be able to let you guys actually use some of these devices, because they've only very recently been released. So we had, and this is one of the reasons why we pushed the date for this workshop back from the originally planned date, because we had ordered a system which had, 12 nodes, I think, with these KNC cards in them. But things didn't really run to schedule, so we haven't been able to show you, but I thought it might be good just to tell you a little bit about this architecture. So before we start, it was only publicly unveiled at the Supercomputing conference in November.